7.1 and 7.2 is on exponential growth and decay. But first, let's look at what an exponential function actually looks like. It is written in the form y equals ab raised to the power of x. Notice that the x value in this instance is the power. There are some qualifications, however. A cannot be equal to 0 because then y is just going to be equal to 0, and I'll show you. So if a is equal to 0, and I just substituted in a 3 for the b value, it comes out to be y equals 0. So that would it does not represent exponential growth or decay. The other qualification says that b has to be greater than 0 but not equal to 1, and I'll show you why it can't be equal to 1. So I chose a random value of 2 to represent a, exponents 0, 1, and 2, but my b values are consistently 1. And every single time it comes out to y equals 2, y equals 2, y equals 2. The equation doesn't change. So the two main points for this lesson is for exponential growth, the b value has to be greater than 1. And for exponential decay, the b value is going to be greater than 0 but less than 1. So it's going to be a fraction. So recall for exponential growth, b is greater than 1. And with all our graphs, we're going to have a parent function. And here it is, f of x equals b raised to the power of x. You might see it as y equals b raised to the power of x. If I subbed in a value, you might see y equals 4x. And here, the growth factor is 4. Okay, that was just to kind of go over what the b might look like. If I had an a value, in this instance, the a value is 1. It's not going to change the value. And the a value will determine if the graph is going to shrink or stretch. But let's look at this graph a little bit more closely. We know that if I had a table of values, x and y, that the x represents the domain and the y is the range. So now if we go down here, it says the domain is all real numbers on this particular graph. So the x values, notice, can be anywhere. It can be in the positive values or the negative values, right? And then if we look at the range is y is greater than 0. So it's any value on the y-axis that's above the origin. Then there's the asymptote. The x-axis is the asymptote because the graph line approaches it closer and closer. So the equation for that line is y equals 0. Here's an example of a basic exponential growth. Y equals 5 raised to the power of x. You can see I chose x values of -1, 0, 1, and 2. When I substituted those values in, I got 1/5, 1, 5, and 25. So now I'm going to plot the x values and my y values. The final ordered pair, x is 2 and y is 25, doesn't fit, but you can see that my graph would look something like this, and it would get closer and closer to that x-axis. So now we're going to switch it up a little bit. I have the same basic equation except for one change. I included an a value of 1/5. So this is going to indicate a vertical shrink. So I start with my original table, and then I just multiplied every y value by 1/5, which changed the y values to 1/25, 1/5, 1, and 5. So now I'm going to plot those points. So far, we have our basic y equals 5 raised to the power of x. Then we included an a value of 1/5, which meant we multiplied my y values by 1/5, and we got new values to represent a shrink. Now I'm going to ask you, what do you think might happen if we included a negative in front of the b value? Well, if we include a negative in front, that means it's going to reflect about the x-axis, and the graph might look something like this. So we have a reflection about the x-axis here, and remember PEMDAS, that we're going to do parentheses exponents, then we multiply, divide, add, subtract. So you're going to work with your exponent first, which gave us the 1/5, and then it's negative 1/5. Translations are back. Remember what we know about the h value. That is a horizontal shift, and the k value is a vertical shift. So if you are given an equation like y equals 2 times 4 raised to the power x plus 2 and then plus 1 to graph, you could graph y equals 2 times 4 raised to the power of x, then do the horizontal shift and the vertical shift. But we're going to do it a little bit differently in this example. There's a lot to look at on this slide. Let's start off with the domain. The domain is going to remain all real numbers. The range, however, is going to become y is greater than 1, and that is because our asymptote is also changing because of this vertical shift of 1. So we are going to draw our asymptote right here. Next, we can see we have a vertical stretch by a factor of 2. So if you remember, we're going to multiply all the y values by 2. Next, we have a horizontal shift 2 units left because of the plus 2. Remember that it's negative h, so double negative is the positive. So that's why we're going 2 left. So this becomes negative 3, negative 2, negative 1, and 0. So moving left to right, we finally got to our vertical shift 1 unit up. So 1/2 becomes 3/2, the 2 becomes a 3, the 8 becomes a 9, and the 32 becomes a 33. So now we're going to plot the green values and the purple values. So a quick recap. If we just took the y equals 4 to the x, and then we subbed in a negative 1, out came the 1/4. If we sub in x equals 0, out came a 1. If we subbed in x equals 1, out came the 4. So that's where the orange values came from, just from the basic equation. Then we went back to the original equation and we worked with the vertical stretch, the horizontal shift, and the vertical shift. Here we have an exponential decay model. A reminder that b has to be greater than 0 and less than 1. So that means it's a fraction, and our b value is 1/3. So we're going to graph where we have a stretch of 2, a horizontal shift of 2, and a vertical shift of 1. So I think you should pause the video, see if you can fill out a basic table, and then apply the stretch and shifts. Because we had a vertical shift of 1, that means our asymptote is going to change, so we should not be crossing this purple line. So y equals 1 is our asymptote. Okay, then we ended up getting the values, our final values that we're going to graph will be 1, 2, 3, 4 for the x values and the purple values, because we started off with the black based upon y equals 1/3 raised to the power of x. So we just took this part. Then we did the stretch of 2, so that gave me the blue values. Then we did the horizontal shift that also happened to be 2, and that gave us the green values. And then our purple values came from the vertical shift of 1. So we're going to plot those. When you plotted the green values and the purple values, you should have come up with this graph. We said y equals 1 is our asymptote. So then our domain is going to be all real numbers, and our range is going to be y is greater than 1. One final note, and we'll talk more about this in class, when we're dealing with growth and decay, for instance, if we were dealing with a bank account, the A represents the initial amount that you deposited, the R represents the rate or percent that you're collecting, and T, the exponent, which we've been talking about as an X, will represent time. And when we're dealing with decay, notice that inside the parentheses, it's 1 minus the rate, so it's going to be a value that is less than 1, whereas for growth it's going to be greater than 1.